Hello everybody, welcome back to my channel, and today we're going to take a look at a paper that talks about, well, what should I say, it's actually a survey of how LLMs can help GNNs in terms of solving graph processing problems. And right now, let's get into it. So, like I say, okay, so in this video, we're going to be going through a survey paper. Now, I know this paper is quite long, and we're just gonna be going through some of its key, um, I would say, key features or maybe key findings. Well, it's a survey paper. Obviously, it is intended for an amateur in this field, such as myself and probably even you. So let's learn together, shall we? And let's start off with the title. Okay, so what we're looking here is a survey of large language models on generative graph analytics, query, learning, and applications. Right. So, okay. A graph is a fundamental data model that can represent different entities and their relationships in many different things, right? So recently we have large language models that showcase a strong generalization ability to handle various natural language processing tasks and multimode tasks to answer users' questions and specific domain content generation. Yep, we all already know that, such as a chat GPT. Okay, compared to graph models, these language models have the advantage of addressing the challenges of generalizing graph tasks by eliminating the need for training graph learning models and reducing the cost of manual annotation. Right. So in this sentence right here, what they're trying to hint to us is that the LLMs could be a new way of generating the text attributes of parts of the graph. At least that's what it looks like to me. So let's go through it further. In the survey, they have conducted an investigation on existing LLM studies on graph data, which summarizes the relevant graph analytics tasks solved by advanced LLMs and points out the existing remaining challenges and future directions. Okay, so obviously there's gonna be a couple of more challenges that we could potentially work together to solve, right? And this paper is going to go through that in a bit more details. But for now, let's just keep on reading. Okay, specifically, we study the key problems of LLM-based generative graph analytics called LLM-GGA, and there's three categories in this area. LLM-based graph query processing, LLM-based graph inference and learning, so graph inference and learning, and applications. I guess these three categories are mentioned uh, on the title itself. But anyway, okay. So the querying processing focuses on integrating graph graph approaches and language model prompts, including graph understanding and knowledge graph. Okay, right. Knowledge graph based augmented retrieval. Right. So nowadays it is quite a common approach, right, to use some kind of a knowledge graph and you put it into an LLM in order to make sure that the LLM doesn't just hallucinate things when you ask it a question. Instead, if we have to go through the knowledge graph and retrieve the most relevant information from the library. All right. And next, we have GIL, graph inference and learning, focuses on learning and reasoning over graphs, including graph learning, graph form reasoning, and graph representation learning. All right. Okay, so they summarize the most the useful prompts incorporated into LLM to handle different graph tasks. They also give a summary of LLM model evaluation, benchmark datasets or tasks, and a deep pro and cons analysis of the LLM models, and it also discuss about some future work that needs to be done in this area. Right. Obviously they are going to go through each of these things one by one. So let's take a look at this figure right here. Okay, so let's take a look at figure one. Okay, figure one illustrates the GGA. GGA stands for generative graph application, right? So that's that. And then, okay, right, and it includes that. Okay, so, right, like I was saying, right, so typically if you have like a question about the graph data and you give it some kind of knowledge graph at the same time, you can feed it into the LLM and that will give you a response. Whereas for graph inference and learning, you feed a whole bunch of graphs into the LM, and then you can either do representation learning on the graphs or reasoning as well. So it isn't exactly clear what the distinctions are between each categories because I can see some overlap in between, but either way, right? Okay, so in this paper, they have an introduction, and then there's a provide preliminaries just in case if you are not used to the terminologies in this area, right? So and after that, wait, is this? Hold on. Okay, so that's section one, and where's section two? Section two is section two. And we have section 3, which directly talks about some of the graph structure understanding tasks. And there's a lot of pages in it. And like I say, there's no way we can go through everything because it's a long survey paper, as you can see. I don't think an hour is even enough. And honestly though, yeah, for me reading a survey paper is try to just have a skim through and then see what the state of the art techniques are in the field, right? Because this is something that I would use a lot for my for my own PhD research, right? So okay, and okay, and section 4 would be on the learning task. Okay, and let's see what else more did I have in here. Okay, this is taking quite some time. Yeah, so like I say, right, there's a lot of things in here. Yeah, so this video is gonna be a bit different because it's a bit more difficult, right? So okay, and we have this section right here, knowledge graph based augmented retrieval, right? So okay, and that's that, right? And they talk about future directions. Okay, how about this, guys? Okay, right, and there's the conclusions, right? Okay, how about this? We go through the conclusion first, right? And then we take a look at the future direction, right? So because those two are pretty short. Okay, conclusion. Okay, what they found out is that a generative graph application with LLM is a promising field of research. So they've categorized it into graph coding processing, graph inference learning, and graph-LLM-based application. So LLM query processing encompasses graph understanding and knowledge graph-based augmented retrieval, while GRI involves graph learning, graph form reasoning, and graph representation learning. Okay, so all right, didn't have anything to say. Okay, right, and say it is observed that LMs show preliminary capabilities in structural understanding of the graphs. Okay, so LMs are able to understand graphs and address issues like maximum flow and bipartite graph matching over small graphs, right? So for those who are not so sure what they mean by that, we can obviously ask ChatGPT about it. Maximum flow in graph theory. What is that? Let's see. Okay, so maximum flow problem is a classic optimization problem where the goal is to find the maximum possible flow from a source node to a sink node. The network is represented as a directed graph where each edge has a capacity indicating the amount of flow that can pass through the edge. Okay, right. So it's kind of like from a source, you have multiple different pipes, right? And each pipe has a different diameter, right? So if you think about it, right, this problem is essentially trying to find a way to like get a lot of water from one area to another, right? So you will have to find out which pipe to use, right? Which connection to use, so that we can maximize the flow of water. Yeah, and I think this has to do with like electric circuits as well, pro- pro- probably in that sense. So yeah, so the fact that the LLM can do this is pretty impressive. Okay, and the other one is bipartite graph matching. So let's see. Okay, bipartite graph matching in graph theory. All right, let's. Okay, so bipartite graph matching is a problem in graph theory. It is about finding a matching in a bipartite graph where the graph's node set is divided into two sets, two disjointed sets, and the edges only connect the nodes from different sets. Okay, so I think a figure would be nice here. Okay, so let's see. Okay, so it's something like this. Okay, right. So maximum flow from source to sink is 5 units. There's a maximum of 5 people who can get jobs. Okay, so essentially, if you have like a set of nodes, right, and then you like cut it into half in order to create two sets of disjointed nodes, right? And then you draw some edges in between each one of them. And that's essentially bipartite matching, is it? So, okay, finding a matching in a bipartite graph okay, right, where this, okay, let me see. Yeah, I don't think that explanation is clear enough. Okay, let me see. How about this one right here? Uh, what does Geeks for Geeks have to say? Right. So a matching in a bipartite graph is the set of edges chosen so that no two edges share an endpoint. A maximum matching is a matching of maximum size, maximum number of edges in a maximum matching. If any edge is added to it, it's no longer a matching. Right. Okay. So okay, I see. So basically what they mean is that of when you draw the edges, right, from one set of nodes to another, right, you right, in order to be matching, the nodes from the other side should not be receiving any additional edges, right? Only one node can only get one edge from the other side of the node. I hope that makes sense a bit. Okay, by converting it to that, yeah. So, okay, right, build a flow network and then finding the maximum blah, blah, blah. I mean, my understanding could be incorrect, but either way, right? Yeah, yeah, I will have to check it out after this video. Okay, right, okay, right. It can do graph matching, that's great. However, it is susceptible to factors such as node degree and graph density, which leads to potential misjudgments in graph connectivity, right? So it kind of doesn't know how to interpret the degree of a node and how dense the graph is, right? But it can also help with graph learning tasks due to its semantic understanding and reasoning capabilities, which is something that the LLM can do and not the GNN, right? So, okay, right, which can provide external knowledge to GNNs. Yeah, right. If you have watched the previous video on my YouTube channel, we have gone through a ton of papers about how LLMs can boost the capability of GNNs, right? Just by giving it additional information that the GNN cannot provide to itself, right? So, okay, so the LLM semantic understanding is cool. Okay, and also, okay, the discussion also goes into knowledge graph-based augmented retrieval that can help out with the LLMs. Okay, and the paper summarizes over 40 data sets, evaluation metrics in 6 directions. Source codes are available as well, so do check it out if you want to. It highlights the existing challenges in the current methods and proposes future directions to guide and motivate research in the field. Okay, that's pretty cool. But I'm now more, yeah, yeah, we should go through uh, the future direction quickly. All right, so let me just readjust some parts of this, right? All right, so let's go through future directions for now. So, okay, so there's a few future directions, sorry. Okay, fine. Right. So, and the first one is can LLM solve graph algorithm problems? Right. Existing approaches of existing works on graph tasks are based on fundamental graph problems, blah, blah. However, can LLMs address NP problems, right? If so, how? And they say that future work needs to focus on this particular problem, NP problems, and then more complex graph patterns, right? So obviously in graph theory, there's a lot of different ways to create a graph, but but trying to get the LLM to understand these variety of different graph topologies is quite difficult, and that's another thing that needs to be solved. So, right, and they say that most existing works focuses on static graphs, but in reality, right, there's like a lot of different types of graphs, such as undirected, directed, cyclic, acyclic, isomorphic, heterogeneous, and dynamic. So yeah, so there's a lot of differences, right? Static graphs, dynamic graphs, temporal graphs, and so on. So obviously there's a lot more work that needs to be done in this case. So things like dynamic graphs and temporal graphs, it's gonna be really good if we can like use the LLM to help us out with these issues right here. But yeah, for now it's something that needs to be done sooner or later. All right. Better LLM GNN pipelines. Why? I wonder. GNNs are designed to handle structural information, whereas LMs excel in reasoning, textual information. So the problem is, how do we properly handle both attributed and pure graphs? And that's what they say. If you only stack them up together simply, right? And they say that the parameter size of GNNs is not just notably smaller, it's like significantly smaller, probably by like 100 times, And this discrepancy mentioned in the issue of vanishing gradients during training can make the training process really bad. Obviously, okay, so this part is interesting. The issue with vanishing gradients. Yeah, I haven't heard about vanishing gradients in so long, and I thought that LLMs and GNNs already took care of this issue, right? Like this issue is most prominent in like with recurrent neural networks, but I'm not so sure why that's the case for GNNs and LMs. But either way, right? That's pretty interesting. So, okay, and what do they have to say? GNNs need to utilize extensive knowledge contained within LMs fully, and they cannot extract specific knowledge tailored for specific downstream tasks. So, essentially, what they're saying is that is it possible for the GNN to select the info from LLM on its own preference, right? Obviously, during training, right? Some kind of a filtering mechanism, right? Something like the attention mechanism in some way, right? Where you can like select what kind of information that you need in order to get better training accuracy, right? That's something for future work. And next, graph foundation model. So LMs are foundation models in language processing, but that suggests, is it possible to train a graph foundation model? And I think there's already one yeah, I think someone has already done that. I forgot. Is it Google or Microsoft? Yeah, it either way that's done, right? But it's only done by like a single company at this point, if I think so. Yeah, yeah. If you guys know, please drop down your findings in the comment below. But I think it's already done. Okay. For example, can training strategies like in instruction fine-tuning and a direct policy optimization be applied for graphs? Ah, man. Um, well, if you say that for the GNNs, purely for the GNNs, I don't think so. I don't think so. Because these approaches are only like applicable for those language models, right? For those human language understanding models. But I don't think it's applicable for graphs at this point. I could be wrong here. The current research has primarily introduced graph foundation models in the form of LLM, GNN pipelines, and graph-aware tuning LLMs. Future endeavors can focus on exploring graph foundation models more suited for tasks involving graphs. Okay, right. And next, better graph prompts. Okay, most graph prompts are currently designed based on graph neural networks, with only a few specific works focusing on LLMs. All right, graph prompts for LLMs have yet been sufficiently explored. This is true. This is true. What the heck? Oh, never mind. Graph prompt for GNNs. And to say, the typical approach uses simple concatenation, addition, or dot product attentions, operations, right, to combine, to fuse those information together, right? So that is something that we can explore a bit more. And also graph enhanced prompts for LLMs, which relies solely on manual prompts and self-prompting is limiting the capability of the model. They say, right? As they only explore the existing abilities of large language models. As shown in some section, LLMs can be trained as agents that uses tools for graph tasks that are hard to solve, like API call or graph of thoughts. It's a graph reasoning paradigm that allows LLMs to provide the correct answer. Future work based on graph reasoning paradigm can consider cost-effective approaches for graph of thoughts, such as pruning and tricks to reduce algorithm complexity. Yeah, so if you guys do not know what GOT is, it is a graph of thoughts, right? It's essentially an extension of chain of thought. No, actually, it's more like the it's more like the predecessor of tree of thoughts, and tree of thoughts is a predecessor of chain of thoughts. You can look for graph of thoughts on archive, but to be honest though, I've been trying to use graph of thoughts for my work, but I couldn't find a really good GitHub repo that has already implemented it, right? So so yeah, it's a shame that I couldn't use it, but I will keep on trying. Next, model alignment. So modality alignment refers to the alignment of text modality and graph modality. The input for LLMs is often text. So they're saying that, oh yeah, these two different modalities, right? How can you find a shared mapping feature for both graphs and text? Well, in some sense, right, this question has been addressed already in a couple of previous videos that I did for this channel, where they essentially create like a linear mapping, if I'm not mistaken, a linear mapping that generates the same embedding dimensional vector, which then you can use for knowledge distillation. But but either way, right? Yeah, but I don't think the work is exactly done at this point. And I don't think there's like an official way of like quantifying how whether or not this problem even exists at all. Yeah, so far from what I have read, it's not really formal, right? It's not a, yeah, I wouldn't say it's not a real problem, but then again, right? I don't know. All right. Next, explainability. Graph neural networks are currently used for a lot of complicated graph problems, but they need to be more interpretable. right, interpretable, and then say that, oh yeah, if we use LMs and GNNs, that can be more interpretable because of the reasoning capabilities, right? And if it's more interpretable, then we know exactly how it works for things like recommendation systems, drug design, and fraud detection. So essentially, with the model being more interpretable, you get to know how it makes those decisions, right? But sometimes being more interpretable would mean that the model actually kind of suck. It is kind of bad, right? Right? Because you sometimes you need to be really complicated in order to get the right answer. Sometimes, right? I mean, it depends on what kind of problems you're dealing with, but either way. Okay, next. Efficiency on large scale graphs. Okay, this is the one that I'm talking about here. So obviously, the larger the graph you have, the harder it is to use LLMs for the large scale graphs, right? Like this passage says here, a larger input window is required, right, for these large graphs, right? How do we even make them? How do we feed these large graphs into the LLM? I have no idea, right? But I could imagine some approach, right? Which I've already seen some people doing is that if you have the LLM right here, you can actually get like a super cheap GNN and trying to feed in an embedding vector into the LLM, whether you use some kind of like cross attention mechanism or just directly feeding in as an input token. There's a lot of ways, right? But either way, it's a question that needs to be solved quickly, right? So yeah, so that's all the complaints and the future studies that they suggest, right? Which most of them make sense right here. Okay, so now what should we do? What should we do really, right? Okay, how about if we quickly skim through everything and we call it a day, all right? So I will primarily look through the figures instead of the text, because the figures usually tell how do I say, right? It's a shortcut, right? Essentially, I don't have to like read every single thing because like this is just a survey paper. All right. So what do you have in figure two? Okay. In figure two, I think they're showing a bunch of different graph structure understanding tasks. So here, okay, calculate the size of the graph, right? And that's the prompt. Degree calculation, connected nodes calculation, edge validation path search, attribute retrieval, graph density, graph diameter, pattern matching, topological sorting, maximum flow, bipartite graph matching, right? Hamilton path, yep, okay. So those are the graph structure understanding tasks, and look at this table right here. Okay, and these are the prompts for the graph structure understanding tasks. We have graph data loading, okay, prompt. The structure of blah molecular graph of benzene ring contains a hexagon. Task. Graph size detection. What is the number of nodes? Blah, blah. Please answer with the number of nodes X, number of edges X. Right, so these are the prompts. I think we saw those a bit earlier. And then here, okay, what's the difference? Okay, prompts where graph is the input. Okay, and right here, it's the same as the above, but instead of just having graph as the input, right? We also have TBR, means to be reasoned by LLMs. So the LLMs have to give their reasoning for their answer. So okay, it's involved in reasoning, form that. Okay, I get it. Sort of. Hmm. Interesting. Interesting. All right. Let's go through the next figure. Figure three. Just a second. Number one. Okay. Figure three. Examples for path tasks. Okay. Right. So what are you trying to do here? Right. Given an undirected graph with these nodes and edges, find a single path from node 0. Okay, pathfinding. Essentially, asking the LLM to do pathfinding. Right, okay, right. So these are the responses. So, okay, in figure 6, they have prompting methods in graph structure understanding tasks. So there's three different things: manually prompting the LMs or make the LM self-prompt itself, and API call prompts. Let's take a look at manual prompting. So given a graph, what's that? What's the property of the graph? Then you feed it into a represent LM. Or for self-prompting, you say, okay, you are someone who's really good at these stuff, and then okay, graph description language, be like this, GML, graph ML, etc. And then ask it a question, and then what it will do is that it will generate new context, text description of input graph generated by LLM itself. So it is sort of like, I wouldn't say self-prompting, it's more like a thinking process, right? It's reflecting, right? It's doing all this all of this thinking, right? And it's yeah, recursively, right? Until at the end of the day, right, you stop the thinking process and you get the final output. I think that's what it means. Okay, next. This one is okay. You give it some question and it straight away just like call for an API. Okay, I really like this approach because it's kind of like cheating in some sense. It's like, oh yeah, I have this really smart AI, but then when you ask the AI to do something, it just directly tells a human to do it. Well, do you think that's a really smart AI? Do you think that's even valid in that case? Well, I don't think so, honestly, right? But you could think the other way around and like say, oh yeah, but it knows how to like select the proper tools to use, right? But honestly though, at that point, who needs AI? Who needs AI, right? AI is supposed to like handle even the most like in detail part, not just this high level overview and that's it. Okay. Okay, and that's built generating a graph prompt. Okay, algorithmic prompt. Okay, right. And there's a lot of things here. Okay, so these are like some of the prompts. Okay, right. Okay, figure 7. Supervised fine tuning. Right. Okay, supervised fine tuning in graph understanding tasks. Prefix prefix tuning. Oh, okay. Right. So this is a very interesting approach. Right. Just give a second. Hmm, hmm. All right. So from what I can see, right, if you have like a few tokens that represent the graph and you feed it into the LLM, you they just fine tune the the embeddings, I mean the neural network part that's responsible for processing those specific graph embeddings and keep the rest frozen and keep the other word tokens frozen, right? Which is pretty interesting to say the least. All right, let's see. All right, what do we have here? Okay, we have reached the next part. Graph learning tasks. Okay, so for graph learning tasks, we have a few of them, right? And so this is very typical in graph neural network papers. We have classifying the type of node that is, right? The identity of the node, or you can even classify the entire graph on itself. And you can classify what type of connection, right? What kind of edge is that? And we have knowledge graph, querying analysis, answering, blah, blah, blah. So you can use knowledge graph, right? And you have your generic graph querying, query learning. And finally, a node feature explanation, right? So explaining why the feature is the way it is for that node. Okay. All right. That's that. I mean, it's nothing new. It's things that I kind of know already. All right. So the prompts are okay for the knowledge graph. Okay, given this graph, who is the director that is responsible for the movie Inception, right? And for this one right here, given a graph, right? Yeah, so these two are basically the same or they're similar, right? All right. Node classification. Which subcategory does this paper and this paper belongs to? So you're just trying to classify. This is a classification problem in the sense, and classifying the entire graph. Given the graph is that molecule active with something, right? H3C4. I don't know what's that, right? So okay, node feature explanation. Okay, abstract question. Which one does it belong to? Give the five lightning. Yeah, I think this part right here, this node feature explanation is something that the LLM does, but not the GNN. Okay, and edge classification, learnable prompt. Wonder what that means. Learnable prompt. All right, let's have a look. Figure 9. They have some pretty figures right here. So node text attribute feeding in into some trainable language models, right? But small and big ones, and also a frozen one. And then getting the text embeddings, and you give it the adjacency matrix, give everything to the GNN. Yeah, so that's basically the LLM does all the pre-processing part, gathering up all the reasoning and the knowledge information stuff, and then feeding it into the GNN. We've seen that a million times already, nothing too new, right? But this one right here is pretty interesting, right? So if you don't have labels for your nodes in the graph, you could potentially ask the LLM to give you some kind of an approximate correct label and use that to train the graph neural network. And that's something we have seen a lot in the couple of previous videos that I did. So if you haven't watched those, you can go and check them out. Check them out in my channel if you want to, but it's all up to you, right? But I don't think it's that necessary here. Well, it really depends, but either way, right? Either way, figure 11. Okay, so let's see. Right, so Okay, right. Providing external knowledge explanations when LLMs act as enhancers to the graph neural network. The pipelines are shown above. In the first pipeline, input text attributes into LM for elaboration in order to make the text attribute more more detailed, right? In the second pipeline, the input text attributes and design queries are placed into the LM, and the LM generates text attributes with respect to the answered queries and explains the reasoning process by the LM. So that's that. Okay. All right. There's a lot more here. Okay. Figure 12. LLMs act as predictors. So right here, we don't use any GNNs at all. Instead, we just use purely LLMs, right? And let me tell you something. It's gonna be tough, um, right? Because like a lot of hallucination, and it's more about generating text rather than for graphs, right? But it's possible to get a decent accuracy, but you wouldn't like expect it to outperform GNNs at any point. I guarantee you that. But either way, I'm telling you, it is possible, right? You can do some kind of supervised fine tuning to the LLMs, but at the end of the day, if you use that data just for the GNN, it would work out even better, right? So, okay, right here, selecting the correct answer, use that as for the instruction tuning, right? So, yeah, nothing new about this really. Um, right, right. This is the knowledge graph, right? And we got some nodes and edges, right? Nodes at the top and the edges at the bottom, right? Describing the relationships. Pretty simple, straightforward, intuitive. All right, let me see about this. All right, figure 15 shows something, right? It shows a graph problem for graph learning. Graph problem method first unify the prefix and the downstream task. Then pre-train graph neural network on the unified task. The pre-trained graph neural network, when faced with different downstream tasks, combines with a tunable prompt with tuning prompts to handle downstream tasks better. Okay, right. That's a lot of words, but essentially you have a GNN and you train it on some task, right? Whether it be from the downstream task or the prefix task. And then you combine the already trained GNN with a tunable prompt, right? And then you can make it work for the downstream task roughly. Um, let me see. Okay, right here. Is this? Let me see. Sort. Okay, let me see. Graph form reasoning task. Okay, right. So this is essentially like I think this is more applicable for the LLMs, right? So you're trying to make the LLMs to perform reasoning by in this graph structure format, if I'm not mistaken. Uh, okay. Maybe there's more explanation in this section right here, right? But yeah, and they show this figure right here. I bet this is to like convey the idea that humans also do this structural form of reasoning as well. Is that we go through each part of the graph, each ideas, right, in a graph style, right? I think that's what it's trying to go for, this approach. Ah, yes, right. Graph of thoughts is somewhere around here, right? So as I mentioned before, it's just trying to emulate what humans usually do, right? So it's what we usually, our thinking process is typically like a graph structure, if you think about it, right? So yeah, but I wouldn't say that it's necessarily new. Obviously, this is a survey paper, right? Okay, let me see. And they have this verification process, verify and verify. So there's two steps of verification. Interesting. Okay. Verify on the graph means using the graph to verify the correctness of the LLM's intermediate and final output. Okay, guys, you know what? I think this part would be extremely useful for my work, right? Because this has a way to ver verify the LLM's output in between, which is something that I haven't think about yet. But anyway, let's continue. Let's see if there's like anything cool down here. Yeah, so and these are some logical questions, mathematical questions even. Mm. Oh, Jesus. I'm getting tired. Yeah, these things are, yeah, there's a lot of them. Wait, hold on. Which section is this? Oh, yes, the final one. Thank God, right? But you see, I have to go through every single one of them because I don't want to miss out on stuff that could be useful for my work. Um, Grab specific order sequences use LMs or PLM. Don't know what that means. Protein language model. And anyway, yeah, graph representation. Okay, right. Let's see. There's a graph embedding, graph enhanced text embedding, and graph encoded prompts. Right. And what we saw above is essentially graph encoded prompts. Right. But typically, right, typically this approach is being used, this one right here, right, where you have the LM creating all those pre-processed information and then you feed it to the GNN. And a lot of times, 99% of the time, the accuracy is going to go up, right? But as for this one right here, I can't really say the same. Yeah. Do you know what this approach right here? It kind of reminds me of this graph former paper. That's right, graph former paper. Where they apply this like a specific order sequences, but then but they induce this sequence information into the attention matrix, and that somehow improves the accuracy, right? So, so it is quite interesting to see that there are significant overlaps in between things that are in between topics or papers that are like far away, even though this is more about using this kind of sequences for the LLMs, but in fact it's also applicable to like graph transformers as well, right? So so that's interesting. Okay, right. Knowledge graph based augmented retrieval. Knowledge graphs can enhance LLMs to provide more correct answers. I think we already know that. There's a lot of videos on YouTube that already talk about this knowledge graphs to to the coffin, but yeah, I'm not gonna talk about any more of that because we know it. So yeah, okay. Anyway, yeah, obviously there's gonna be they mention a lot of different approaches. Okay, here. Okay, figure 21. Sorry, figure 22. Right. Graph LLM based applications recommendation system. Right. So essentially, if you have some kind of a graph data from your company or whatever, you can then feed it into the LLM and then fine tune it by using low rank adaptation so that you can fine tune it without having to empty your wallets for those GPUs. Yeah, and that's that. And graph LLM based applications. Okay. So this paper is incomplete. Double question marks. Okay. So, all right. And they also, and obviously they provided a lot of so they curated a lot of different models and different approaches for graph tasks using LLMs. So yeah, and they also specify what kind of LLMs that they use and also what kind of tasks they use, and they also provide the link to every single one of these approaches, which is cool. Thank you for that, authors. Um, okay, and it also describe well the data set that they use. Right. A summary of new data sets. Okay, they wrote it as if it's their own data set, but no, it's actually other people's data set. And it's a shame that some of them are to be released when I highly doubt it's going to be released at all in the future, right? Unless they're going for publication, then maybe that's another thing. Yeah, and the evaluation metrics, that's all cool. All right. All right. Cool, 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 cool. So, yeah, I hope you guys learned something new from this video. Well, for me, it's just to make sure that, like, I didn't miss out on anything crucial because I'm directly working in this field and I need to get to know, what are the state of the art approaches out there, but anyway, yeah, if you like this video, please make sure to like and subscribe. Or if you have anything to say, please leave it down in the comments below. And I will see you guys in the next one. Bye.